A potter's wheel having a radius of 0.5 meters and a moment of inertia of 12 kilograms times meter squared is rotating freely at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim and exerting a radially inward force of 70 newtons. Find the effective coefficient of kinetic friction between the wheel and the wet rag. The first thing I went ahead and did is I listed the given values that we had. R being the radius, I being the moment of inertia, both omegas being the initial and final angular velocities, and t being time. Next, I went ahead and drew two pictures, a before picture and an after picture. One with the potter's wheel spinning at that angular velocity, and the second one with it slowing down from the wet rag. The next thing I went ahead and did was I wanted to find the angular acceleration. So from last chapter we learned the angular acceleration is equal to the change in angular velocity divided by time. So the next thing I did after that was I converted, because this is in revolutions per minute, this is what's given to us. We want to convert it to seconds in order to get how many radians per second we're going to, in order to make it fit this equation. So 50, we just convert it using some dimensional analysis, and we get approximately 5.24 radians per second. So since the final angular velocity is 0, we're going to get a negative angular acceleration here. So it's approximately negative 0.873 if you plug it into your calculator, radians per second squared. Next, I used the torque formula. We had I alpha, torque is equal to I alpha, which is also equal to RF, the radius being R and F being a force. And there's also a negative there. And this is to indicate the direction of the force. Because this is going if you think about it, this is going clockwise. This angular acceleration being negative. So that negative is there, and it works out nicely for us. So the force, if you isolate for F, you get approximately 20.94 newtons. So this force that we found turns out to be the frictional force. So if you think, this is how I thought about it. There's a rag being applied here. There's an angular acceleration. But this external force, I think we talked about this in class, there's this external force on the cylinder. And that's what makes this problem a little bit difficult. It's not a straightforward problem. You have to take the external force into account. So I used a little equation here. The sum of forces is equal to the external force minus the normal force that's from that. Oh shoot, here we go. So we can conclude then that the external force is equal to the normal force of that external force. So then we can say that the frictional force is equal to, this is from chapter 4, is equal to mu times, which is the coefficient of friction, times the normal force. So if we isolate mu, we get the force, frictional force divided by the normal force, and mu comes out to be approximately 0.30.